All right, hi, this is Mr. Bates. I'm going back to record a little bit of voiceover after the fact. It turns out my volume was quite a bit down for the first several minutes of this. So this is me later in the evening coming back with a little bit of voiceover for you all. Welcome to our review session. We're going to start today with kinematics as our first unit. So thank you very much for coming, and let's get started. So the idea here is we're going to be we're going to kind of do the same thing for each section. The first thing we're going to be doing is we're going to be looking at the sorts of equations that come up quite a lot. You've done a lot of kinematics over the course of the year. So you've probably seen, our 1/2 AT squareds come up a lot, right? We've got some of the other equations we've seen, like, root 2gh for the velocity, different things like that. So there's some equations that we should be able to get used to and see more often. So we're going to start by looking at key relationships and equations, figure out when it's kinematics, when should you use your kinematics equations, and figure out what to do, how to select the right equations that we might need to use in this case. So we'll do with our overview, again, talk about those key equations and relationships, and then we'll get a few multiple choice questions that have been requested off of our review packet. Now I'm waiting for my past self to do something. All right, here we go. So we're going to start off, of course, with the kinematics equations. You'll see them kind of in two different versions here. Kinematics is all about the relationships between position, velocity, and acceleration with respect to time. And you want to make sure we remember all of our units here, of course, with respect to time. Kinematics is really all about these time relationships in this case, right? Meters per second squared. So we're always looking for how these things change. So when we're looking at our three kinematics equations here, we of course have that first one where final velocity equals initial velocity plus acceleration times time. That first equation is going to tell us how our velocity changes with respect to time. If we're accelerating, how are we speeding up? Are we slowing down? One of the ways that we're always going to be able to rewrite this is if we kind of slide the initial velocity over to the other side. We'll end up with, sorry, I was having a little bit of trouble with my pen. You'll see in a moment, if we slide our initial velocity over to the other side, we end up with this idea that it's just, our change in velocity, delta v, equals a delta t in this case. And that's kind of our core relationship. One of the important things to mention here is, of course, that our kinematics equations really only ever work when we have constant acceleration. We have to have constant acceleration. So for our second equation here, that's the 1/2 AT squared, that's the big one. This is going to tell us, instead of how our velocity changes over time, how does our position change over time if we're accelerating? That is, if we've got accelerated motion, where are we at a given time? Because it's always, if you're speeding up, a little further than you expect, or if you're slowing down, not quite as far as you expect in this case. The third equation is the one that has no time in it whatsoever. That's the one that just doesn't include time. It's actually secretly not a kinematics equation at all. It is actually a forces and work equation, but we still use it here as a kinematics equation. That last one, that third one, of course, is our v final squared equals v initial squared plus 2a times our displacement. Quick reminder, of course, while I'm waiting for my past self to catch up, you can always use these in x or y. They all say x here, but it's just, you can use them in any direction that you want as long as you are consistent. You don't want to mix your x's and y's here. There is a last equation that you can use in there. There's me saying that's the one with no time in it, no t in it. There is a last equation you can use, which I'm going to kind of obscure in a moment and replace with a different one, to remind us that our average velocity during an interval is, for accelerated motion, if our acceleration is constant, our average velocity, which is usually total distance divided by total time, our average velocity is in fact the average of our initial velocity and our final velocity. So you're gonna see me write that up in just a moment. There it is, our v average, which is delta x over delta t, right? Total distance over total time. We can also write as initial plus final divided by 2. And that is not one you actually need, but it can be handy at times. People tend to confuse that average velocity for the initial or final, but it's in fact right in the middle in this case. One important thing to think about is the relationship sometimes with graphs. So if we're looking, and here I'm making an argument about average velocities. If I go from 10 to 30 meters per second, my average velocity is right in the middle there. It's 20. Again, assuming my acceleration is constant. If my acceleration is non-constant, then we can't use these equations. Yes. One of the other things we always need to consider is we need to consider the relationships between position, velocity, and acceleration on graphs. So we have this little graphic here to remember that if I start with my position or my displacement, if I have a graph of that, the slope of it is my velocity. The slope of a velocity time graph is my acceleration. If I want to go back up, if I have an acceleration time graph, it's going to pop me back up to velocity. If I have a velocity time graph, the area under that is going to give me the displacement. And there is a question on the review packet that asks, hey, what if I have a position time graph? What is the area under that graph mean? And the answer is it actually means nothing whatsoever. See if that helps at all. If we want to go back up this, we use the area under the graph. So again, the most common application for this is to get a velocity versus time graph, and we need to look and find the area under that curve to get the displacement. There is a question on the review sheet about what the area means on a position graph, and the answer is it doesn't mean actually anything at all. It's not a thing you're interested in. Not a thing. When you're trying to pick your kinematics equation, we always want to ask that question of what do you have and what do you need, right? So take a look at what the question is asking you for. Is it asking you for an acceleration? And what do you know? Do you know an initial, a final velocity? What information do you have? And that network of what you have and what you want is what's going to guide you to choose. All right, I do want to take a moment to talk about projectile motion. Projectile motion being the special case of something being launched through the air. The most important thing to realize is that in two dimensions, in two-dimensional motion, x and y, we can separate out the x motion and the y motion. So when you're setting up your kinematics equations, it's really, really important that you say, okay, this is an equation in the x direction. I'm only using x quantities. This is an equation in the y direction. I'm only using y quantities. And the reason for this is the motions are very different. In the x direction, we have no acceleration. Gravity doesn't act in the x direction, and as a result, in the horizontal direction, our acceleration is 0, and that means that our x velocity is constant. We're not speeding up, we're not slowing down. Our x velocity is totally constant, and that makes the motion in the x direction really easy to analyze. The motion in the y direction is basically falling motion. The thing might have some initial velocity, but it's just accelerating downward. There's a whole bunch of equations here that we'll go over more deeply in class, and all of these are derived using different ideas. So here's me drawing arrows to represent how the x velocity never changes, but the y velocity does. The y velocities might start out positive and end up negative. So whenever we're analyzing this motion, there's really only ever two cases that they're going to give you. Even though you've got this kind of general idea here, the two cases that they're usually going to give you here are going to be either symmetrical motion, so it takes off from the ground and lands on the ground, the initial y and the final y are the same, or you're going to end up in a position where you're getting launched horizontally. Now, either way, the apex of your flight is really important to note, and that's the place where your y velocity is equal to 0. Your x velocity will not be 0 because, again, your x velocity never changes. So finding your y velocity is really, 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 really important, or finding when your y velocity is equal to 0 is really important. And we're going to set up in a moment an equation for doing that, for getting the, there we go. Right, if I set up my first kinematics equation, my final y velocity at the apex is 0. My initial is whatever it is, minus gravity times time. So I can solve pretty quickly for this idea that the time it takes me to get up to my apex is going to be my initial y velocity just divided by gravity. There's a lot more of me, past me talking here, I assume. Right. Again, most often our motion will be symmetrical. We're taking off from the ground and landing on the ground. In which case, it's important to note that the time that it takes to go up to the apex and the time that it takes to go down are the same, or should be the same. So that is always a helpful thing. Either that, or we're going to get launched horizontally off of a cliff, in which case our initial motion is purely in the x direction. That is, our initial y velocity is 0. If it ever says I get launched horizontally, our initial y velocity is 0. There's a bunch of other equations here that are really important, and we will go over them more deeply in class. So if I'm, quite often if I'm just falling, that I'm 1/2 at squared, right, if my initial velocity is 0. So a couple of these equations only depend on our initial velocity being 0. All right. You don't need to know all of these equations off the top of your head. It's really just having some facility with the kinematics equations to say, well, I'm going up to a place where my final velocity will be 0, or once I get up to the apex, coming back down, I'm starting from 0 velocity, so I can just use 1/2 at squared. All right. How do I actually know when to do kinematics is a really important question. The most important thing here is that it involves time, especially in relation to distance, velocity, or acceleration. Where are we at t equals 4 seconds? How fast are we going? How long does it take to do x? Time is the hallmark of kinematics. Obviously, if they say projectile motion, if a thing is launched or dropped or anything, then it's almost certainly projectile motion is always kinematics. If they leave out mass, it's usually kinematics, although obviously there's some forces questions where you don't need mass. It asks specifically for acceleration or velocity. They just love to throw in kinematics to FRQs. You know, a thing rolls down a ramp and then falls off the table. So now it's a projectile motion question. And again, we just want to make sure. We often forget to use 1/2 at squared. All right, let's get into the actual multiple choice questions, starting with number 1. Here we have two graphs where it asks us to figure out which object is furthest from the origin. Well, we have a velocity time graph here, so we're always going to be looking on a velocity time graph at the area under the curve. So if we look at object A, here I am making a graph. If I'm looking at the area under the curve for object A, well, it goes at +1 meter per second for 1 second, and so the area under there is going to be 1. And if I look at the second for object A, it's now traveling backwards at -1 meter per second for 1 second. So I get a total area of +1, and then I'm going to make the argument in just a moment and draw it up on the board thingy that I have an area of -1. Here we go. There we go. There's -1. Now, as it turns out, +1 -1 works out to be 0. So object A actually ends up back where it started in this case. Object B, on the other hand, I don't know exactly what the area under object B's curve is, but I know that it's not 0, and so anything is bigger than 0. So it turned out to be B. Here we've got a question now about about the Hot Wheels car, and we want to look at the graph here. Again, this is an area under the graph sort of thing. If I look at the first little bit here, I'm going in the negative direction, and that's a triangle. It's got a base of 1 and a height of -1, I guess. So it's got an area of -1/2. Oh, I'm making an argument about how not to be tricked. So it goes -0.5 meter in that first second. There we go. So we're now 0.5 meter behind the origin, so we need to make up for that. So between 1 and 2 seconds, we go +1 meters. So somewhere in between 1 and 2, we end up where we want to go. And I'm going to circle that in just a moment. I love waiting for past me to do things. There we go. Good job. Now if you look at the numbers I've got in red, I've got a 1, a 2, and a 1, which is closer to 4. -0.5 gives me 3.5. This next question is 100% a kinematics question, and it's all about just using your kinematics equations straight up. So we start at 0 at time 0. We start at the origin. Between 0 and 1 second, we just have a nice constant speed of 24 meters per second. So I'm going to draw that in a moment, but what that does mean come on, we can draw. There we go. So at x equals 0, here's my tomato. We're at position 0. Moving at 24 meters per second. So after 1 second, we go, well, 24 meters. Come on. There we go. $24 meters. 24 times 1, as it turns out. But after that 1 second, the tomato is given a constant acceleration of 6 meters per second squared in the negative direction. All right, and here I'm going to tap out and hand off to past me. Take it away.
Testing, is that better? How's that? Okay. Sorry about that. Thank you for letting me know. I'm using I'm in a different classroom than usual. All right, so here we are. We got this tomato moving in the positive x direction. It passes through the origin at time 0. And at time 1 second, it's at 24 meters. It goes 24 meters per second for 1 second. 1 second, it's then given a constant acceleration of here of 6 meters per second squared in the negative direction. So let's just go ahead and draw this. Here it's got a velocity of 24 meters per second, but now it has an acceleration of -6. And we want to find where it is at time equals 11 seconds. Well, this is a classic second kinematics equation sort of problem, because it's asking for an object undergoing some acceleration. Where is it? And that's what the second kinematics equation is made to do. So let's write out that second kinematics equation and then fill it in. Plus 1/2 AT squared. Well, we want to find where it is. In this case, it's a little bit non-obvious. I want to start my thinking after 1 second. And the reason I want to start my thinking after 1 second is because all of the kinematics equations depend on the acceleration being constant. And in this case, the acceleration is not constant. We have no acceleration for 1 second, and then all of a sudden we have some. So we're going to start at t equals 1 second. And if we start at t equals 1 second, well, in that case, I'm starting here at a position of 24 meters. Cool. My initial velocity is still 24. I haven't started slowing down yet. And I'll leave a big suggestive blank for the time. Plus 1/2 AT squared. Now, in this case, I want to be a little careful. My acceleration here, right? Am I speeding up or slowing down? I'm slowing down. So I want to make sure to put this in as -6 meters per second squared. Because if you think about it, my velocity is going to want to carry me in the positive direction. My acceleration wants to carry me in the negative direction. The last thing that we need to ask is, it wants to know 11 seconds. But of course, we're starting at 1 second. So how much time are we letting pass? How much time are we letting pass here? 10 seconds. Yeah, exactly. We already did the first second. By going from 0 to 24. And at this point, we just have to do some calculation. So this will be 24 plus 240 minus, well, that 10 squared will be 100. It'll be minus 300. And I believe if you do this out, you end up with -36 meters in this case. This is calculationally a little bit more complicated than I might expect, but I think it's still a good trial for that kinematics knowledge in this case. And again, for those of you joining us online, of course, we did 1 or 2 questions. We can always go back, or you can look at them in the video later. But if you have questions, please feel free to speak up or drop something in chat, and we'll if there's a question we didn't cover, or you're not sure about something, this is of course your time. The next most popular question was number 9 and 10. And so here we're starting to move into projectile motion. So a really important topic that it's been a while since we've done. So here we've got a diver that is moving initially horizontally. So remember, if they're moving horizontally initially, that means it's only x velocity at first. The initial y velocity is 0. And they follow a certain distance d. So I want to remind ourselves, right, that in the x direction for projectile motion, there's absolutely no acceleration. So the distance that you go is just your x velocity times time. Your x motion for projectile motion is really simple. So then it asks, how far from the base of the cliff would the diver land if he started with an initial speed of 2 times v? Well, let's think about it. If you double your x velocity, right, what does that actually affect? Clearly, it doubles your velocity, right? You've doubled your speed. Does it affect the amount of time it takes for you to hit the ground? No, it doesn't affect the amount of time it takes for you to hit the ground. The time it takes for you to hit the ground is entirely a question in the y direction, and it doesn't change anything about the y direction. So time comes from hitting the ground in the y direction, and doubling our horizontal speed doesn't affect that. So double the speed, same time, just gives us twice the distance. I'm realizing, by the way, I fixed it in the online version For number 10, it says as shown, and there's no picture on your packet. But this is the picture if you want to draw it. For number 10, we've got a target lying flat on the ground, 3 meters from the side of the building that is 10 meters tall. And it asks, how fast do we have to roll it off for it to hit the target precisely? What's that initial x velocity in order to hit the target precisely? Now, in this case, we want to look at this from, again, this question of the distance that it goes is the x velocity times time. And since we want the x velocity here, that's going to be distance divided by time. Well, we already know how far it goes in the x direction. It goes 3 meters. So the real question is, how long does it take to hit the ground? And to figure out how long it takes to hit the ground, we got to switch gears to the y direction. Let's look at the y direction for a moment. We know a couple things in the y direction, right? In the y direction, it goes 10 meters, right? We know the acceleration in the y direction is, 10 meters per second squared, or you can always use 9.8. You'll always have it as most nearly. So if you use 9.8, you pick whichever number is closer. And in this case, the really important thing to note is what's our initial y velocity in this case? They don't give it, and that's actually really important. What they do say, though, is we come off horizontally, right? So if at first we're coming off perfectly horizontally, then our initial y velocity is 0. Just for that first moment, we're going purely in the x direction. Of course, we immediately start to fall. But anytime we say it comes off horizontally, you can assume the initial y velocity is 0. And so in this case, we're asking, we've got a distance, an acceleration, and initial velocity. We're looking for a time. The only one of the kinematics equations that links all of those things is the second kinematics equation. So we can say, well, it goes 10 meters. This is 1/2 at squared. T squared. Let's see, we can do this. So 1/2 of 10 is 5. 10 divided by 5 is 2. T squared equals 2. That makes t equal to √2, which is about 1.4 seconds. And if we do that division, if we take that time now and bring it back up here, 3 divided by 1.4 seconds is, I think I literally covered it over with the, yeah, I definitely did exactly cover the one answer that is correct with my picture, which is a little over 2 meters per second in this case. A little over 2 meters per second. So in this case, we need to make sure that we're looking at the x direction, we're looking at the y direction. It can be a little tough sometimes to figure out for projectile motion what you need, but here they want an x velocity. So you've got a distance, you need a time. Usually with projectile motion, time is the crux. Time is the thing you need to find. How long does it take to do a thing? All right. Speaking of time, here are two more one more projectile motion, a different one. This is also, number 13 is also a projectile motion question. So here, we've got an arrow aimed horizontally. So I'm going to assume that the person is a competent archer, and that initially they're aiming for the exact center of the target, which is 20 meters away. In this case, right, the arrow that they fire impacts, it doesn't hit exactly, it falls as it goes and impacts the target a little low. It impacts the target 0.05 meters below, 5 centimeters low. And then it asks, how fast was the arrow going? That is, and again, because it says horizontally, what it's asking for is the initial x velocity in this case. The initial x velocity in this case. Well, once again, we need the initial x velocity, which is going to be the x distance divided by time, because again, it's nice and constant. It doesn't speed up or slow down in the x direction. Similar to the other one, we once again know that it goes 20 meters, but we got to figure out how long it takes. Well, this is actually precisely the same as the other one, because what we do know is in that time, it falls 5 centimeters, 0.05 meters. So what we can do is we can once again set up our 1/2 AT squared, 1/2 GT squared. If you like the symbolic stuff, this is where we early in the year had derived this equation. You multiply by 2 and do some stuff. That the time for it to fall is √2h over g. Remember, that only works if your initial y velocity is 0, but our initial y velocity is 0 in this case. So if I calculate this out, my time to fall here, 2 times 0.05 divided by, I'm again using 10 here, is it takes 0.1 seconds. It takes 1/10 of a second to hit the target. Well, once I know that it takes 1/10 of a second to hit the target, how fast does it have to be going to do 20 meters in 0.1 seconds? Well, that's going to be 200 meters per second in that case. For that one. 14. There's actually a couple different ways to do 14. One way to do this is, you could do it the long way. You could find the time it takes to fall and everything. You could say, oh, well, gravity is 10. In order to get it going up to a speed of 30 meters per second, it should take about 3 seconds to fall, and do it that way. You could also do it using our third kinematics equation, right? You could say, well, my v final squared equals my v initial squared plus 2 times my acceleration times my distance. So this is going to be, my final velocity is 30 squared. I started, whenever it says dropped, if it doesn't specify otherwise, that you can assume it's dropped from rest, plus 2 times g times the height of my building. So again, here, my height is going to be my final velocity squared divided by 2g. So that's going to be what, 900 divided by 20, which I think should be 45 meters in this case. We can always check it. You could also do this by the energy route, where, if it's dropped from rest, the final velocity should be √2gh and go from there. If you prefer energy to kinematics, some of these questions definitely can be done in more than one way. All right, let's get to the last couple. There's a car question, and then some more, a more complicated projectile motion question. So here we've got, and we've seen this kind of question quite a lot. Sometimes it has a picture. We've seen it a few times on quizzes and things where they just give you a table of positions versus times. I guess they usually give you time first or whatever. They give you some data. And then they ask you a bunch of questions about it. The important thing to realize is that if it's accelerating, you want to make sure to use 1/2 AT squared, right? So in this case, we know that it started from rest. So our initial velocity is nothing. And otherwise, we know all of the position data. So if I come and look at my last point here, what I could say is, well, I know that the final position is going to be equal to 1/2 AT squared, because again, normally that equation has a v0 term in it, but if the initial velocity is nothing, it's just 1/2 AT squared. So here I can say, well, it goes 0.96 meters, 1/2. I don't know what my acceleration is, but I do know that it takes me 0.4 seconds to do that. And here, if I do my algebra properly, 0.96 times 2 divided by 0.4 squared, I should find that my acceleration, you can solve for this, my acceleration is 12 meters per second squared. Actually, quite an aggressive acceleration in this case. So it accelerates quite quickly by the standards way, doing a 1/2 AT squared. For 16, what was the instantaneous velocity of the cart after 0.4 seconds? That is, we're asking for the final velocity. And again, this is where people tend to get a little tripped up. What often happens is people will look at a question like one of these and be like, I see a distance and I see a time. And so they'll do 0.96 meters divided by 0.4 seconds. And they'll get 2.4, which I was nice to you and I didn't actually put on the list. Sometimes they will. Here's the problem. This is not your final velocity. this is your average velocity. This is your average velocity. Average velocity is kind of, if I didn't start from rest, if I just did the whole thing at one constant speed, how fast would I have to go to do the same total distance in the same total time? Remember, average velocity, you're kind of looking at our velocity versus time. You know, we have an initial velocity and a final velocity. Average velocity is right in the middle, assuming our velocity is changing at a constant rate, is exactly halfway in between. So sometimes you can use a handy trick, which is it actually is going to turn out that the answer is going to be 2 times the average velocity. But the better way to do this is to say, hey, I know that we start at rest. So my final velocity here is going to be acceleration times time. I know I've got a 12 meter per second squared acceleration times 0.4 seconds, which gets me 4.8 meters per second. Right? Notice that that is in fact exactly twice the average velocity. The reason for that is that, again, assuming constant acceleration, average velocity is initial plus final divided by 2. It's literally the average. But if my initial is 0, right, it starts out at rest in this case, well then this is just half of my final velocity. So sometimes you can exploit that trick. You can find the average velocity and then double it. Not every time, but it does work out sometimes. All right. Last 2 in this section. Let's take a look at this. This is a projectile motion question in 2 parts. So let's go ahead and draw it out. And again, I always suggest you draw things out. It's really helpful. So here we've got a projectile fired from the surface of the Earth at 200 meters per second. We've got an initial velocity of 200 meters per second at an angle of 30 degrees. And it says the ground is level. And what that means is it goes up and comes back down to the same height. And the first question it wants us to figure out is, what is the maximum height reached by the projectile? All right, well, let's do this the methodical way. So the first thing that we want to do is we've got a velocity, we've got an angle. Let's break this up into some components, shall we? So instead of just a general initial velocity, let's get an initial velocity in the x direction and an initial velocity in the y direction. V0, y. Now, being able to find these components is really important. In this case, it looks to me like the x velocity is our adjacent side, so we're probably going to use cosine. Absolutely. So this is going to be 200 times the cosine of 30 degrees, which, assuming I'm in degrees mode, is like 173.2 meters per second. If I do the y velocity initial, that's going to be 200 times the sine of 30. That one's a lot easier. I happen to know, of course, that the sine of 30 degrees is 1/2. So it's got a y velocity of 100 meters per second. It's always good, by the way, to gut check yourself to see whether you've done this properly. 30 degrees is not a very steep angle, right? I mean, it's not nothing, but it's more flat than it is not, right? So we end up with a larger x component than a y component, which I think makes sense if you visualize a 30-degree angle. All right. So here we're looking for height. We're looking for a distance in the y direction. And what that means is, remember, all of our calculations, therefore, should be in the y direction. If we're trying to calculate something in the y direction, everything should be in the y direction. And again, here we got to remember, we're trying to find the height of that apex of that maximum point. And the most important thing about that maximum point, that apex, is that at that point, the y velocity is equal to 0, right? The y velocity is equal to 0. There's a couple of ways you could actually do this. I don't know if you're interested in looking at it more than one way. One way you could certainly do this is you could find the time that it takes to get up to the top. And as we mentioned earlier, one way to figure out the time that it takes to get up to the top is to say, okay, well, I know in my y direction that my initial velocity is 100 meters per second. And I know also that my acceleration in the y direction, I'm just going to use 10 instead of 9.8, is negative 10 meters per second squared. It's trying to pull me down. And that my final y velocity is 0. Well, if I've got two velocities in acceleration, and I would like to find a time, I can actually use my first kinematics equation. The first kinematics equation is a great way to find your apex, because it says that my final velocity equals my initial velocity plus acceleration times time. So I can just say, hey, well, if I start at 100 and I slow down at a rate of 10, how long does it take me to stop? Well, I think we can eyeball this and find out that it should take us 10 seconds to get up to our apex. It should take us 10 seconds to get up to our apex. And if it takes us 10 seconds to get up to our apex, what we can do then is we can say, aha, well, now I know it takes 10 seconds. How far does it go? Well, turns out I have an equation for that. Y equals V0yt plus 1/2 at squared. You just got to be a little careful filling this in. This is going to be 100 meters per second times 10 seconds plus 1/2 times negative 10 times 10 squared. That's going to give me 1,000 minus half of 1,000. So 1,000 minus 500 should give me a maximum height of 500 meters. There is another way to do this, which doesn't require finding time at all, although it turns out the time will be helpful. The other way to do this is you could look at your third kinematics equation and say the third kinematics equation, V final squared is V initial squared plus 2 times our acceleration times our distance. And we could say, well, we end at a velocity of 0. We started at a velocity of, well, I'm going to solve this out symbolically. V0 minus 2gh. And we basically end up with our maximum height here being V0 squared over 2g, which will also get you to 500. You could, in theory, do it with conservation of energy also in the y direction. You just got to make sure you only find the kinetic energy associated with the y motion in this case. For the maximum range, this one's actually a lot more straightforward for the maximum x distance, because our x motion, remember, is a lot simpler. It's just our x velocity times time. The x velocity never changes. Well, we've already got the x velocity. It's 173.2 meters per second. The question is, what's the time? If it takes 10 seconds to get up, how long does it take to get back down? 10 seconds. It's nice and symmetrical in this case. We land at the same height we started. If it takes 10 seconds to go up, it takes 10 seconds to go down. And as a result, we multiply this by 20 seconds. And we get a big number of meters. It goes nearly 3 kilometers, so 1.5 miles. Is that right? About 1.5 miles. 2 miles and change. It's a fun random fact, by the way, about miles and kilometers. This has nothing to do with physics. It happens that the ratio of miles to kilometers is about the same as the golden ratio, which means nothing, but it comes up in the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13. Basically, you can use this to estimate. 5 kilometers is about 3 miles. 8 kilometers is about 5 miles. 13 kilometers is about 8 miles. If you ever need to do that kind of thing. Oh, excellent. Yes, exactly. If we redefine the length of a mile, the golden ratio will change, and then we'll have to fix all the means. All right, so I'm sure there will be more questions about kinematics. Kinematics is again, the big challenge with kinematics is just figuring out which equation you want. And I would just be very careful to think about what you have and what you need. So with that, let's turn our attention quickly. Well, we'll do a quick summary and then we'll turn our attention to forces. Again, for your equations, just remember you've got those 3, right? The first one tells you about how velocity changes with time. The second one tells you about how position changes with time. And the third one is the one that doesn't involve time at all. So that's how I'd like you to think about that. If you want to know where something is, use the second. If you want to know how fast it's going at a certain time, use the first one. If you don't have time or you don't need time, the third equation is your friend. And just a quick reminder on how you kind of use graphs on that as well. All right. Yeah, of course. Let's turn our attention then in the second half here to forces in this case. Forces, or dynamics as it's called in here, is a really important subject as well. Lots of free body diagrams and things like this. So as we did for kinematics, let's talk about some things that come up a lot and how to identify some of these key things. So again, just like I said for kinematics, the same kinds of equations come up over and over and over and over and over again. We see some patterns develop, and it's always good to try to exploit those patterns to find yourself some shortcuts if they work for you. I cannot stress enough how important it is for you to draw a free body diagram. Like, take 5 seconds on your exam, on the corner of the exam when you're taking it, and just be like, oh, okay. Without the drawing, it's extraordinarily difficult to understand dynamics and forces. The drawing really helps you. So again, we're going to look at some key relationships and equations for forces, remind you about drawing free body diagrams, and then how do you know when you should do a forces question versus how do you know when something's a forces question? All right, so key things to remember. The first thing is Newton's laws, right? First law, an object at rest stays at rest, an object in motion stays in motion, right? If there's a net force equal to 0, then what that means is that the velocity vector is constant. Anything that changes your velocity, whether that's speeding up, slowing down, or even turning you at a constant speed, requires some kind of force. Remember that if your net force is 0, we call that being in equilibrium. You can be in static equilibrium, that is, you're not moving. You can also be moving at a constant speed if all your forces are balanced. They will most often cue that something's in equilibrium by saying that it's moving at constant speed or constant velocity. An important thing to note. Of course, the big one is the net force equals ma, F net equals ma. You really got to know that one, and writing down the net forces tends to be the hardest part there. Newton's third law, remember that equal and opposite forces, it does not matter how crazy this scenario is, right? If I have the entire Earth or the entire moon crashing down on top of you, the force that the moon applies to you is the same as the force you apply to the moon. Now, that force probably hurts you a lot more than it hurts the moon, but the actual forces are precisely equal and precisely opposite, and that's really important to know. Also remember that these Newton's third law pairs always appear on different free body diagrams. So this is the force of moon on you. This is the force of you on moon. So one of these appears on your free body diagram, the other appears on the moon's free body diagram. There's lots of different kinds of forces. Gravity, right? Remember, typically we say gravity is just mg, and that's how we calculate it. That is also the weight. So if they straight up give you the weight of an object or ask you about the weight of the object, they're asking about gravity. Tension, remember, tension is on these strings and ropes, and it is always considered to be the same at both ends of the rope. It always pulls inward, and it's always equal on both ends of the rope. Friction is really important. Remember, the force of friction, the force of kinetic friction is always equal to mu times the normal force. The force of static friction can have a variable value up to the maximum of mu times the normal force. Often they will ask you about, about like limiting cases. What's the minimum coefficient of friction? What's the most friction you can get? So typically they're going to ask you to max out static friction and make it equal, but remember that static friction can take on any value up to mu times the normal force in this case. There are two different mu's, right? Mu k is typically weaker than static friction mu is typically weaker than kinetic friction mu. Springs come up, that force is kx in the restoring force direction. And we have actually broken off centripetal forces into their own units, but remember still, when you're dealing with forces that you need a centripetal acceleration of v squared over r, which means you need a net force in the radial direction of m times a, mv squared over r, or m, if you're doing rotational stuff, m omega squared times r. Couple other things that you might have forgotten about: inclined planes. Remember that for inclined planes, we care about a direction parallel to the ramp and a direction perpendicular to the ramp. That's how we're going to set up our Newton's second law. You've got to have these memorized, like 100%. Mg sine theta versus mg cosine theta. So I remember sine for slide. Sine is the one that points down the ramp. Cosine is the one that opposes the normal force. In all of these cases, no matter whether it's an inclined plane or not, you're always going to draw your free body diagram, pick your directions of motion, and then write out your Newton's second law in that direction. Atwood machines, we're going to do a little bit of pulleys and Atwood machines. Remember, pulleys kind of bend your coordinate system. So one way to think about that, right, is if I've got two masses like this, when the hanging mass falls, the other mass is going to move to the right. So my positive direction of motion is sort of this way. You can think of the pulley as being a magic pulley. It bends your coordinate system around it in this case, when you're setting up your Newton's second law. Quick note, the AP exam almost always wants you to draw full vectors, not components. So if you have an object that's sitting on a ramp and it asks you to draw a free body diagram, the free body diagram you should draw should look like this. I mean, okay, let's assume it's sitting still. You've got static friction this way. You should not draw your components of gravity. They will say vectors, not components. Do not draw components. If you need to draw the components to help yourself out, here's what you should do. Draw the thing that they want in the place that they want it. And then off to the side, in the margins, you can draw, okay, well, I really need mg sine theta, mg cosine theta, right? Go ahead and draw your components off to the side, but do not draw them on the official free body diagram under any circumstances. How do I know when it's a forces question? How do I know when there's a forces question? Well, it involves mass, acceleration, or sometimes it'll just be like a force F. A lot of times we need to use forces also for statics, objects that are not moving, that are suspended by strings or different things. Free body diagrams are explicitly invoked. Sometimes they'll be like, this is the free body, which of these is the free body diagram? Draw a free body diagram. That's clearly forces. Friction is always forces. I guess sometimes it's energy, but it's almost always forces. Inclined planes, springs, all this kind of stuff. Rotational motion, you always got to have forces involved. And again, a key phrase you always want to look out for is constant velocity. They drag something at constant velocity. They move up a hill at constant speed, because that will tell you that your net force is equal to 0. I was about to circle that, but it's not statics. This is dynamic equilibrium. So if they tell you, oh, a car is driving at constant velocity, well, what that means is that whatever force is pushing it is counterbalanced by some other force, probably some kind of drag force. So just important things to realize. All right, let's take a look at a bunch of multiple choice questions. And the first two here are actually of a piece. They are very similar. And the way in which they're very similar is that they both involve systems that have multiple parts. There's like two blocks connected together. It's really important with these systems to kind of go from a big view to a small view. So what I would do is I would start at the big view. I would say, what is our total external force? And what's the total acceleration of the system? And so let's take this first one as an example. We're pulling this system with a force F. And yeah, there's a string, there's two blocks, it's a little bit weird. Let's imagine for a moment, let's ignore the fact that they're connected. We've got a 1 kilogram and a 2 kilogram. Well, okay, we're not ignoring that they're connected. Let's ignore the string in the middle. We've got a 1 kilogram and a 2 kilogram. That force F, if we imagine putting a big box over this whole thing, that force F is basically pulling something that has a mass of 3 kilograms. We have a total force of F pulling a 3 kilogram mass. So the acceleration, right, F equals ma, tells us that the total acceleration of our system is F divided by 3. Now, I'm going to wait a moment because I'm not ready to circle an answer. The total acceleration of my system is F divided by 3 kilograms. Is F divided by 3 kilograms. So now I want to open the box. And I want to look for a moment at my 1 kilogram mass. And I'm going to look at my 1 kilogram mass, and I'm going to say, okay, my 1 kilogram mass over here in green, my 1 kilogram mass in here only has one force on it. It has this tension force on it. It's got this tension force on it. And so the question is, I need that tension force. I need that tension force to provide an acceleration of F over 3. I need it to provide an acceleration of F over 3. And so if I think about this, well, I know 1 kilogram, and I know my acceleration I solved for here is F over 3 kilograms. So what I'm going to get is, okay, 1 times F over 3 is not surprisingly F over 3. Let's think about that for a moment, right? Let's think about that for a moment. This is getting a force forward of 1/3 of F. The other box, which we'll make into a yellow box, the other box has 2 forces on it. It's got a force F this way, and it's got a force, remember the tensions are the same, of F over 3 this way. Well, I know F minus F over 3 is going to be 2/3 F. So the net force on my yellow block is 2/3 F. But of course, it's twice as massive, so it still accelerates at the same rate. So the whole key of these connected problems is that the 2 objects accelerate at exactly the same rate, and those internal forces work themselves out to be whatever they need to be to make sure that both objects accelerate at precisely the same rate. The 2 kilogram object gets twice as much force as the 1 kilogram object does in this case. They kind of, you can sort of think of it as divvying up the full force F. This gets 2/3, the other one gets 1/3. Here's a very similar question here, which is got a little bit more numbers in it. So you've got 2 blocks being pushed along by a force of 20 newtons. Let's just pause for a moment and say, again, this looks 3 kilograms plus 2 kilograms. This looks like a 5 kilogram system. If I apply a 20 Newton force to a 5 kilogram system, I'm going to get an acceleration of 20 divided by 5 of 4 meters per second squared. My system is going to accelerate at 4 meters per second squared. Now, let's open up the box. We know how much it's accelerating. And now it's asking the force that the 2 kilogram block exerts on the 3 kilogram block. Well, we got to be a little clever here. We're asking, the question is asking for this. It's saying, okay, my 3 kilogram block has a 20 Newton force this way and some unknown force this way. Well, what we could actually do is we could be a little clever and be like, oh, well, thanks to Newton's third law, I know that that mystery force is exactly the same, that mystery force is exactly the same as the force being applied to my 2 Newton object, or my 2 kilogram object, excuse me. And my 2 kilogram object, that's the only force on it. So here's my question. If we look at F equals ma here, how much force does it take to get a 2 kilogram object to accelerate at 4 meters per second squared? Well, 2 times 4 is 8 newtons. So the answer here is that the 2 kilogram block exerts on the 3 kilogram block a force of 8 newtons. 2 the left. Here's where we do have to make sure that the 3 kilogram block is being pushed to the left. Notice this one ends up with the blue block ends up with a net force of 8 newtons. 8 divided by 2 is 4. Let's take a quick look just at the red block to double check. The red block has 20 this way and 8 this way, which gives it a net force of 12 newtons. Well, 12 divided by 3 is also 4. So the 2 blocks work out that internal force to make sure that they both accelerate at the same rate. So if you've got one of these problems with multiple objects in the system, what you should do is figure out the total external force and use that to find the total acceleration of the system. And in fact, that's an approach that can be used for more complicated things such as Atwood machines. We, way back when, did a slightly more complicated system of equations approach to Atwood machines, which still works. Let's see if this works. So let's take a look at our modified Atwood machine here for number 4. We have a block of mass 3m attached to a block of mass m. There's no friction or anything. And it wants to know the acceleration of the system. So here's my question. What is the external force that is making our Atwood machine move in number 4? You can type it in chat or something. What's actually making the system move in number 4? Gravity, absolutely, gravity. Right, there is a string here, but the string is an internal force. It's relating the 2 blocks. The external force here is gravity. So the total external force here is mg. Here's the thing. What's the total mass of the system? That mg force needs to move the whole darn system. What's the total mass of the system? Oh, no, we're talking about number 4, not number 5. 4m. Yep. So it turns out, okay, these go away, divide by 4. My acceleration is going to be g over 4. For these modified Atwood machines, they do expect you to be able to do this. You might also remember if we did this back in the day where we had this as m1 and this is m2. And we figured out that the acceleration of the system was m1 times g divided by m1 plus m2. Note that in this case, if we apply that equation, that still works. We get mg over 4mg. And we get effectively the same thing as we did before. For our normal Atwood machine here, where we've got we've got a mass on both ends, let's see if we can take the same approach. So let's look at the total external forces acting on the system here. Well, again, ignoring tension, tension's an internal force. What we're going to have is we're going to have 60 newtons worth of gravity down here, and we're going to have 40 newtons worth of gravity down here. Here's the question. What is the total force in this case? Is the total force going to be 100 newtons, or is the total force going to be 20 newtons? Am I going to add them, or am I going to subtract them? And as you're thinking about your answer, I want you to imagine what the system would do if it were 40 newtons and 40 newtons. Oops, just took my pen apart. If it were 40 newtons and 40 newtons on either end, what would my system do? Yeah, it would do absolutely nothing. So in this case, what we can do is we can say, well, 60 newtons is trying to pull it this way, 40 newtons is trying to pull it the other way. So here we can say the net force on our system is going to be 20 newtons. But the total mass of our system is going to be what? How much mass is it trying to move? 10 kilograms. So our acceleration here is going to be 2 meters per second squared, which last I checked was 10 divided by 5 g over 5. I guess you could have left this as 2 times g rather than 20 equals 10a. We had also arrived at an equation for this one that is good to know. For this kind of an Atwood machine, if we've got m2 and m1, our acceleration ends up being m2 minus m1 all over m2 plus m1 times g, which is still philosophically what we did. So you can obviously try to remember the Atwood machine equations, and we can go over during class exactly how to derive those. But they're fundamentally derived from looking at the total external force and finding the acceleration, right? We have m2g minus m1g as our net force, but it has to move the total mass of our system still. All right. Here we got some ramp questions. Ramp. Ramps are great. The magnitude of the normal force. Remember, of course, that the magnitude of the normal force here, if we kind of sketch out our free body diagram, mg, we are going to have some friction in this case, Fn, some friction. Normal force is going to be balancing out the perpendicular component of gravity, which is mg cosine theta. Here's mg sine theta. I just want to be clear here, right? Sometimes they want you to use your calculator to calculate sines and cosines. Let's just remind ourselves here the normal force is going to have to be equal to mg cosine theta. And the reason they have to be equal is, again, our box is not going this way or this way. It's just moving perfectly parallel down the ramp. So those two forces have to balance. In this case, we know what mg is. The weight here is 20 newtons. Let's try to be a little clever about this. Remember, cosine, so ca. This is adjacent. Cosine is adjacent divided by hypotenuse. Well, if this is my angle, my adjacent side is 4, and my hypotenuse is 5. The cosine of 37 degrees is approximately 0.8. I think the inaccuracy here is that technically this is 36.9 degrees, not 37 degrees. But in any case, we can do 20 times 4/5 and get 16 newtons there for our normal force. For the second bit here, we want to be a little cautious. It accelerates down the ramp at 3 meters per second squared. We want to find the coefficient of kinetic friction. Well, let's just start by doing some F equals ma and look at the net force in that parallel direction. We've got some mg sine theta pulling us down the ramp, and we've got kinetic friction in this case, which is going to be mu times our normal force up the ramp. And we know that that's going to equal ma. Notice we don't actually need the mass of the box because it's in literally every term. So we can get rid of that. So let's take a look. G times the sine of theta. Again, I'm going to use this trick that sine is opposite over hypotenuse. So the sine of this angle should be 0.6, 3/5. So I should get G times 3/5 minus mu G times 4/5 equals our acceleration. But we know our acceleration is 3 here. This requires a little bit of algebra. G times, let's see, 10 times 0.6, that'll be 6 minus 8 times mu equals 3. So now it's a matter of solving this. We get 6 minus 3 is 3 equals 8 mu, or mu is 3/8. And if you do mu 3/8, it's 0.375 in this case. So we do, in fact, have to look at the forces that are pulling us down the hill and figure out what the coefficient of friction is to get our acceleration just right. All right, we had here, this is a statics question. They do a lot of this suspension thing. And this is maybe obviously a forces question because it literally asks you what the tension is. Here it's asking for the tension in string 1, the horizontal string. So let's quickly sketch out a free body diagram. Of course, we've got mg down. We've got T1 this way, and we've got T2 this way. In this case, tension in string 1 is a little interesting because the tension in string 1 is actually opposing the x component of T2. So T1, the thing we're looking for, is going to be equal to T2, the x component of T2. Well, if I look at my angle theta here, this is going to be T2 times the cosine of my angle. Cool, so if I can figure out T2, I can figure out T1. Well, let's look at T2. T2 has a second component, which is this y component. Let me switch my colors up here. A second component, which is this y component. T2y. And in this case, T2y has to balance out. What does it have to balance out? It has to balance out gravity. All right, and so here's how we're going to do this. We're going to work backwards. We're going to say that whatever my tension in that string T2 is times the sine of my angle. Well, my angle is 30 degrees, and I happen to know that the sine of 30 degrees is 1/2. 5 kilograms times G is 50 newtons. So if half of my tension is 50 newtons, well, if half of my tension is 50 newtons, then I'm pretty sure the tension in my string T2 is 100 newtons. And if the tension in string 2 is 100 newtons, I can go ahead and calculate the x component by doing T2 cosine theta. So I'm going to plug that in. 100 times the cosine of 30 degrees gets me 86.6 newtons in this case. So these two have to be equal, and these two have to be equal in order for the whole thing to hang together. Right, statics are great. Net force is equal to 0. It's all about drawing your free body diagram. All right. Speaking of free body diagrams, here we've got, this is actually a question off of an old multiple choice Monday that you might recall. We've got a student that's moving a box across a rough floor by pulling on it with some force at an angle theta. I'm going to do this question 2 ways. The first way is going to be the brute force way, and the second one is going to be the explanatory, quick, intuitive way. So let's just draw our free body diagram. We've got mg down, this pulling force F0 up. We're also going to have some kinetic friction force this way. And it's going to be important here to consider the 2 components of F0. We'll have an F0 cosine theta this way, and then F0 sine theta this way. So the very first thing is, of course, all of these start with F0 cosine theta, because that's the component of our force that's pulling in the right direction. So they're helpful to us there. They give us good answers there. Then the question is, we got a decision point, minus or plus. Well, there's a mu in there, and mu tends to make me think of friction. So what do we think? Is friction going to be helping us or hurting us? Is friction going to be adding to our acceleration or subtracting? Plus or minus? What do we think? Yeah, subtracting, I agree. The other way I can think about this is I've got my F0 cosine theta in one direction. The only other force is in the other direction. So in this case, it is in fact going to be subtracting. So minus mu. Now here's the question. We've got this kinetic friction force, which we know is equal to mu times the normal force. So let's pause for a second and ask what the normal force is. Oh, I actually forgot something on my free body diagram. There is, of course, a normal force up from the ground. I forgot that one. My bad. The normal force here, if we look at our Newton's second law in the vertical direction, we end up with Fn plus F0 sine theta equals mg. Why does it have to equal mg? Well, the 2 forces up have to equal the force down. So in this case, my normal force is actually going to be mg minus F0 sine theta. That is, what's happening is that I'm pulling up on the box a little bit. Because I'm pulling upwards on the box a little bit, it's lightening my normal force very slightly. My normal force is decreasing very slightly. You could also just track the two minuses that way. Okay, well, this minus is because friction is always hurting you. This minus, in this case, is because the upwards pulling force is going to lighten our normal force in this case. Excellent. 14 is one of my favorite questions. That said, it is a little bit strange. So let's go ahead and take a look at this real quick. I don't know if you've ever been on one of these rides. They're pretty fun. What's happening here is though that you get pinned against the wall. So let's draw a little free body diagram for you. You've obviously got mg down. But then you need two other forces. You need some kind of force pushing you inward because, of course, you are moving in a circle. And because you're not falling, you also need some force pushing you up. Yeah, that's fair. That's fair. So this is a little unusual in that the force that is pushing you inward on the ride is the normal force. And the force that is pushing you up is static friction. So let's start with this. The normal force here is the only thing pointed towards the center. So in fact, this has to be providing our centripetal force. I'm going to go, because we've got a revolutions per minute, I'm going to go with the omega squared r version of the normal force here. Actually, I'm going to do everything symbolic first. So m omega squared r is going to be the normal force here, because remember, our centripetal acceleration can be v squared over r, but it can also be omega squared times r. So there's our normal force. Our normal force is providing the centripetal force. Well, in this case, static friction needs to be equal to gravity in order for us not to slip. And the important thing to note here is that it asks for the minimum coefficient of friction. That is, if friction is as weak as possible, that sort of means conversely that static friction is maxed out. Static friction is working as hard as it possibly can. So here we're going to write mu times the normal force equals mg. And so what we find is that the mu that we need is mg divided by the normal force. And here I'm going to plug in for the normal force m omega squared r. Our m's cancel. So we get g over omega squared r. And the only thing we got to do here is make a little conversion from revolutions per minute into radians per second. So 45 RPM, if my calculations are good, is about 4.71 radians per second. And then we know all the other numbers in this case. So I get here the minimum coefficient is 0.056, which is actually not that high. So I guess it doesn't take that much friction in this case to keep you in place. So this one's a little bit strange, probably more complicated than you'd see on the exam, but that's okay. Speaking of things that are less complicated than they look, number 15 is one that was actually from the forces exam a while back, and is surprisingly not that bad. So the system is at rest, and box A is fixed in place. Which of the following expressions represents the magnitude of the force exerted on box A by box B? Remember, because of Newton's third law, we can ask for what's the force of B on A. We can also ask for the force of A on B, and they'll have the same magnitude. Opposite directions, but the same magnitude. Well, let's actually take a look at box B. Box B only has two forces in the horizontal direction. It's got this force that we're interested in, and it's got a tension force. If everything's at rest, those are equal. If we zoom over to C, C only has mc times g down and tension up. And if everything's at rest, that's equal. So we've got mcg being equal to tension. but tension also being equal to the force of A on B. And we know that the magnitude of the force of A on B is the same as the magnitude of the force B on A. So as a result, that force is really just opposing the force of gravity on C. The force of gravity on C is the only other external force in the system. So how hard do we need to push back? Well, exactly the same as gravity is pulling on box C. So complicated looking question, but not that bad in the end. That brings us to our final multiple choice question for dynamics here, which is elevator questions. And there's a couple other ones. Number 10 is a similar question. And the thing that I want to tell you is you've got to think about the free body diagram, and you have to remember gravity. So here we've got a turtle of given mass sitting on a scale. The normal force on the turtle is found to be 5 newtons. What is the acceleration? You got to be careful, because the temptation here is to be like, oh, there's a force of 5 newtons times 0.7 kilograms, F equals ma. Let me go ahead and divide and get my answer. And the problem is that we'll give you a number, but it's wrong. Why is it wrong? Well, let's look at the free body diagram. The normal force is 5 newtons. Okay, the way the free body diagram has been drawn here for us is a little misleading. The normal force is 5 newtons. What's the force of gravity? What's the force of gravity going to be here? We got a mass of 0.7. Gravity's 10. Seven newtons. Well, we got 7 newtons down, 5 newtons up. That means the net force is going to be not 7, not 5. The net force here is going to be 2 newtons in the downward direction. 2 divided by 0.7 here. So we get an acceleration of 2.86 or so, 2.85, 2.86 in the downwards direction. That is, the normal force is weaker than gravity here. So our turtle is in fact accelerating downwards. So you got to be really careful. Don't forget gravity unless you're in a situation where you're pretty sure you can ignore it. Don't forget gravity. Think about it this way. If the scale was reading 7 newtons, that would mean that there were 7 newtons down and 7 newtons up, and our guy wouldn't be accelerating at all. So this is bringing us to the end of dynamics. And again, the thing that I really want you to remember here is the most important thing is drawing the free body diagram. Sketch it out, figure out what the forces are. Pick your directions of motion and then write Newton's second law. The most important thing is being like, oh, it's going to be, Fn plus mg equals whatever, or Fn minus, mg cosine theta, like whatever your free body diagram says, writing out F net force equals ma is the most important skill in this whole thing. Be thoughtful, right? If your vectors are in opposite directions, they get subtracted. If I have 2 vectors in one direction, right? If I have A, B, and C, then my net force will be A plus B minus C, right? Make sure to consider all of your vectors. This tends to trip people up, especially on those normal force questions, where we've got some component that's pulling up. We got to be like, oh, well, our normal force plus the y component of whatever that force is minus gravity has to equal 0. 2 up and 1 down. So make sure you're capturing every single force from your free body diagram when you're writing out your Newton's second law, and you're going to be okay. You're going to be okay. All right, that's all I got for today. We will be spending some time in the block period this week looking at Unit 1 and delving deeper into some questions that you might want to look at. But otherwise, thank you so much for coming. I will put up the recording, and take care. Have a great day.